All right, so we've stated the three parts of the spectral theorem. Remember, the spectral theorem is a theorem that applies to Hermitian matrices. The first part says that the eigenvalues of any Hermitian matrix are guaranteed to be real. The second part says that eigenvectors of a Hermitian matrix coming from different eigenspaces are guaranteed to be orthogonal. And the third part says that every Hermitian matrix is guaranteed to be diagonalizable. So those are three parts of one theorem. And what's really cool about linear algebra sometimes is that complicated multi-part statements can be elegantly summarized with one equation. And so an alternative way of stating the spectral theorem, if you don't want to do it in three parts, is to state it like this. A matrix H is Hermitian if and only if H has what's called a spectral factorization. So what is a spectral factorization? A spectral factorization is an expression that takes our Hermitian matrix H and writes it as U times D times U conjugate transpose. U here is a unitary matrix, which means that its conjugate transpose equals its inverse. And D here is a real diagonal matrix. If you think about what the parts of the spectral theorem are saying, well, if every Hermitian matrix is diagonalizable, it means that it's possible to diagonalize every Hermitian matrix. But we also know that the eigenvalues of a Hermitian matrix are real. So when we diagonalize a Hermitian matrix, D will have a real diagonal. And also, the fact that the eigenspaces are orthogonal to one another means that it should be possible to choose bases of our eigenspaces that are orthonormal, which would guarantee that the columns of U would be orthonormal, which means that U is a unitary matrix. So the spectral theorem can be summed up in this one cool factorization. So this is called a spectral factorization. And how do we construct the columns of U? Well, the way we construct the columns of U is we go to every eigenspace and we apply the Gram-Schmidt procedure. Remember, Gram-Schmidt takes any basis of any space as an input, and then as an output, we get an orthonormal basis for that space. Cool. So let's look at an example. Here's an example of a real symmetric matrix S. And this matrix S, we actually saw this previously, its eigenvalues are known to be 3 and 6. And not surprisingly, we find that the geometric multiplicity of 6 is 1, and the geometric multiplicity of 3 is 2. What's not surprising about that is that the sum of those geometric multiplicities is 3, which is the size of our matrix. That's the statement that this matrix is diagonalizable. But now the question is, how do we get a spectral factorization? Well, what we need to do here is we need to apply Gram-Schmidt to each of the two eigenspaces. So let's see how that plays out. So remember, when we get a spectral factorization, the spectral factorization will say that S is U times D times U conjugate transpose, where U is unitary and D is real diagonal. Well, let's start by looking at the first eigenspace here, where lambda equals 6. Well, here we only have a basis consisting of a single vector. And if you think about it, applying Gram-Schmidt to one vector is really just the same thing as normalizing that vector. So the normalization of 1, -1, -1 is that vector divided by its own length, which is √3 in this case. So Q1, which would pop out of the Gram-Schmidt process, would be 1 over √3, -1 over √3, -1 over √3. Okay, so that is our first normalized basis vector for our first eigenspace. I'm going to put that in as my first column of U. Now, that first column of U came from the eigenspace of S, where lambda equaled 6. So the first diagonal entry I put in D should be 6. And now if you think about it, U here is, or I'm sorry, on the right here, the inverse of U is U conjugate transpose. So I actually don't need to do any work to invert U. I just need to take that first column and input it into U conjugate transpose as the first row. Great. So that's our first column of U, our first entry on the diagonal of D, and our first row of U conjugate transpose. Now let's go to our second eigenspace and apply Gram-Schmidt. Well, the first thing we're going to do is we can normalize our first basis vector. The normalization of 1, 0, 1 is 1 over root 2, 0, 1 over root 2. That can go in as our second column of U. And since that vector came from the eigenspace of S where lambda equals 3, the second diagonal entry of D will equal 3. And now the second row of U star will be whatever that column was. 1 over root 2, 0, negative 1 over root 2. Great. So we have 2 columns of U now, 2 entries on the diagonal of D, and 2 rows of U star. We're almost done, but now comes the hardest part. We need to go to our second basis vector of our second eigenspace here, where lambda equals 3, and we need to finish the Gram-Schmidt procedure. So what we want to do is we want to take this vector, 0, 1, negative 1, and subtract off its projection onto the previous vector. Well, when we do that, we end up getting Q2, which is 1 over root 6, 2 over root 6, negative 1 over root 6. So I did the algebra on paper at home, and then I'm here to give you the result. But you should double check this if you're uncomfortable with the Gram-Schmidt procedure. What do we do with that vector now? We take that vector, so this is Q2, and we put that into the third column of U. But remember, that vector came from the eigenspace of S where lambda equaled 3. So the third diagonal entry of D will be equal to 3. And finally, our last row of U star will be that vector. 1 over root 6, 2 over root 6, negative 1 over root 6. And this completes our spectral factorization. We applied Gram-Schmidt to each of the eigenspaces. We used those normalized orthonormal bases to fill our columns of U and our rows of U star. And then we input the appropriate eigenvalues in the appropriate order onto the diagonal of D here. So this is our first spectral factorization. One thing to appreciate about spectral factorizations is that here we are diagonalizing S, but since U is unitary, I don't even have to work hard to invert U. So that's pretty nice. And again, this is guaranteed because the matrix S we're working with is a real symmetric matrix, and every real symmetric matrix is an example of a Hermitian matrix. To finish the lecture, I want to apply the same procedure to something that isn't real symmetric. Here we have a matrix H, and this matrix H is Hermitian. It's a 2 by 2 matrix where the off-diagonal entries are related by conjugation. 1 minus I conjugate is 1 plus I. Well, I went ahead and I found the eigenvalues. Unsurprisingly, the eigenvalues of this matrix are real numbers because this is a Hermitian matrix. The eigenvalues here are 1 and 4. The eigenspace for H, where lambda equals 1, is spanned by the single eigenvector, 1, negative 1 minus I. And the eigenspace for lambda equals 4 is spanned by the single vector, 2, 1 plus I. So now I want to use this data to construct a spectral factorization. Well, to do this, I need to fill up the columns of U, fill in the diagonal of D, and then fill up the rows of U star. Where am I going to get my first row or my first column of U? Well, I apply Gram-Schmidt to my first eigenspace, but again, here the eigenspace is one-dimensional, so Gram-Schmidt only really requires me to normalize my first vector. Well, the length of 1 minus I is root 3, so I'm really just dividing this vector by root 3. So the first column of U will be 1 over root 3, and then negative 1 minus I divided by root 3. The first entry on the diagonal of D now will be 1, that's the eigenvalue, and then the first row of U star will be that vector, 1 over root 3, negative 1 minus I divided by root 3. How do I get the second column of U? Well, the second column of U will come from the second eigenspace. I want to apply the Gram-Schmidt procedure to my basis here, which again, because this is one-dimensional, is just the same thing as normalizing. The length of this vector is what? Root 4 plus 1 plus 1, so root 6. So I want to divide these entries by root 6. 2 over root 6, and then 1 plus I divided by root 6. That vector becomes my second column of U. Then the second diagonal entry of D will be lambda equals 4. And then the second row of U star is our vector here. 2 over root 6, and then 1 plus I over root 6. And since this is 2 by 2, I'm done. There's nothing else to do here. So this gives us our spectral factorization of, in this time, our Hermitian matrix that is not symmetric. But again, this is provided to us, or this is guaranteed to exist by the spectral theorem. This example is actually going through the mechanics of producing the spectral factorization, which is guaranteed to exist by the spectral theorem.